Hello and welcome back to Counting Rocks, an Introduction to Combinatorics at CSU. Today we're going to be talking about combinatorial proofs, another proof technique in combinatorics, and my favorite one. The most common type of combinatorial proof is a technique called counting in two ways, and it's a very simple sounding principle. If a set A has m elements and it also has n elements, then m equals n. So if you count something in two different ways, and you get m the first way, and then you get n the second way, well then those two numbers have to be equal. So this is a good way of proving equalities, even in algebra, by just thinking about counting, which is really fun. Here's an example. Very simple. Let's count squares of an A by B grid in two ways. Well, if you draw the rectangle this way, we usually do A times B, because it's A by B, so we make a choice of A rows and then a choice of B columns, so that's A times B. And written this way, if we turn it sideways, then there's B rows and A columns, so we might choose one of B rows first and then one of A columns. And so we'll get B times A. So this in some sense is a combinatorial proof of why A times B equals B times A. Another sort of more general way of saying it using the multiplication principle is that if you choose one of A things and then one of B things, that's the same number as choosing one of B things and then one of A things, because it doesn't matter what order you choose them, there's still A times B. So this is a combinatorial proof of the commutativity law of multiplication. Let's look at something a little more complicated involving choose. Now, we've shown this identity algebraically before, but let's give a combinatorial proof that n choose k equals n choose n minus k, which is the vertical symmetry of Pascal's triangle. So n choose k is the number of choices of a team of k people from n people. To get started with a counting in two ways proof of an identity like this, what I usually do is I think of something that one side of the equation counts, and then I try to count it in a different way that gives me the other side. So starting on the left-hand side, n choose k is the number of choices of a team of k people from n people. This is just one possible interpretation. Of course, you can choose k flavors of ice cream out of n that are, distinct or something like this. But in this case, let's just choose one set. And now we want to try to figure out, why does n choose n minus k also count that same thing? So in this case, n choose n minus k counts the number of choices of which people are not on the team of k people. So to choose a team of k, you could also just say, I'm choosing this team of n minus k who are not on that team, they're on some other team. So both count the choices of a k-person team from n people in two different ways, and so they're equal. Let's look at another proof of this same identity. Like I said, you can make any combinatorial interpretation of one of the sides and try to show that the other side counts it too. So I chose k people from n at first, but we've also seen another interpretation of n choose k. n choose k is the number of binary sequences with k zeros and n minus k ones, because you have to choose where to put the k zeros. And I like this interpretation because then you can just think, well, you can also choose where the ones go as well. If there's k zeros, there's n minus k ones. And so n choose n minus k is also this number of binary sequences with k zeros and n minus k ones, because once you choose which positions out of n have the ones in them, the zeros go in the other places as well. So let's do another example. Remember that the sum of the rows of Pascal's triangle are the powers of 2. Like 1 plus 4 plus 6 plus 4 plus 1 is the fourth power of 2, 2 to the fourth, which is 16. In general, we saw that n choose 0 plus n choose 1 plus n choose 2 up to n choose n equals 2 to the n. And we proved this with the binomial theorem. This can also now be proven by induction using the methods in the previous video. And today we're going to prove it combinatorially with a counting in two ways argument. Let's set up a combinatorial proof by first looking at the simpler side, 2 to the n, and remembering something that 2 to the n counts. Let's go with the number of subsets of 1 through n. When we did subsets, we remembered that the number of subsets of 1 through n is 2 to the n, so let's use that as our set that we want to count in two ways. So we know that one way of counting it gives 2 to the n. Each number can be in the set or out of the set. But how can we see why this sum of choices also counts the same thing? Well, the left-hand side counts the number of subsets of 1 through n that are either size 0, because n choose 0 is the number of ways of choosing no things out of 1 through n. n choose 1 is the way of choosing a size 1 subset out of 1 through n. n choose 2 is the number of ways of choosing a size 2 subset, and so on. And each subset is either size 0 or size 1 or size 2 or up to size n. And when we use OR, we use the addition principle, so we add all of those together. And so this also counts all of the subsets, because every subset has some size between 0 and n, depending which elements you choose as your subset. So this is a combinatorial proof. We've shown that the subsets are counted in two ways, either by this formula or that formula. And so the two formulas are equal. Let's look at one more example of this. the sum of the first n powers of 2 has a nice closed formula. If you add up 1 plus 2 plus 2 squared plus 2 cubed up to 2 to the n, this is a finite geometric series formula, and it's equal to 2 to the n plus 1 minus 1. Let's try to prove this identity with a combinatorial proof. First, I'm going to look at the right-hand side since it's simpler and try to make some set that it counts. Well, 2 to the n plus 1 also counts subsets of something, but there's a minus 1 in here. So let's say we're counting proper subsets of the set of numbers from 1 up to n plus 1. A proper subset is a subset that doesn't have all of the elements in it. It only has some of them. So you can't use the full subset 1 through n plus 1, so that subtracts one possibility off the total. So certainly that's an interpretation for the right-hand side. And now, can we break this down into n cases that gives us this sum on the left-hand side? So here's how we can think of it. There are 2 to the n subsets that don't contain n plus 1. They're certainly all proper. And then among those containing n plus 1, well, there's 2 to the n minus 1 that contain n plus 1 but don't contain n. And we need to filter this way because so every subset either doesn't contain n plus 1 or does contain n plus 1. So once we've done this case, we don't want to overlap it anymore to use the addition principle. So let's now look at the rest of the cases all contain n plus 1 for sure, but then let's say they don't contain n. And then let's say they contain n plus 1 and n, but don't contain n minus 1. Well, then there's 2 to the n minus 2 because we're choosing a subset of the first n minus 2. And we keep doing the cases in this order until we insist that it contains n plus 1 down to 2, but doesn't contain 1. And there's only one such subset, the numbers from 2 to n plus 1. So this is actually a full case breakdown, and so every possible proper subset is in one of these cases, which you can see cover all possible cases by just what's the sort of biggest number that's not contained in it. That's how we're doing the case breakdown. And so that gives us the sum of the two powers on the left also counts the proper subsets of the set of numbers from 1 to n plus 1. Now there's one variant on counting in two ways that's a little bit more complicated, and sometimes you need this more powerful tool, called a bijective proof. Bijective proofs involve two sets instead of one set. Counting in two ways is you count one set in two ways. But bijective proofs is you count two sets and you show that they have the same number of elements. So the principle is if there's a bijection between A and B, then size of A equals size of B. A bijection is a one-to-one and onto correspondence between two sets. It can be thought of as a function from one set to another. So here I've drawn two sets in blob notation. This one has 4 elements and this one has 5 elements. So there's not going to be a correspondence between the elements. But to understand what these words one-to-one and onto means, let's look at them visually. One-to-one means you're not allowed to have 2 points matched to the same point over here. They have to, 2 points in the first set have to go to different points in the second set. So let's fix that. Now we have a one-to-one map. We've uncrossed these. It's okay if the arrows cross, but these 2 points go to different points now. This is a one-to-one mapping, but it's not onto. Onto means everything over in the right set is pointed to by an arrow, and this extra point is floating out here, so it's not onto. So these two sets are not in bijection. If we get rid of that point, now we have two sets that have a bijection between them, and the bijection consists of the arrows that you draw. So once you have a bijection between two sets, it's a perfect matching, and the two sets have to have the same size. So let's see this in practice. Here's a bijection between subsets of 1, 2, 3 and binary strings of length 3. So you can actually match them. We know they're both counted by 2 to the third, or 8, but you can match them in a bijective way that you can construct that can generalize to all subsets in binary strings, where the empty set goes to 0, 0, 0. The set containing 1 goes to 1, 0, 0, because I'm going to put a 1 in the first position whenever 1 is in the set, and I'll put a 1 in the second position whenever 2 is in the set, and a 1 in the third position whenever 3 is in the set. But I put zeros otherwise if the elements are not in the set. So for instance, 1, 3 is represented by the string 1, 0, 1 because there's 1s in positions 1 and 3, and a 0 in position 2 because 2 is not in the subset. So this is a bijection because you can go backwards. One way of checking if you have a bijection is to see, can I reverse this matching and make sure that for every binary string I have, that does determine a unique subset. And certainly, if you have a binary string like 1, 0, 1, then you can decode what that subset must have been uniquely. That means everything over here is pointed to, and there's only one thing that points to it. And let's do one more example of a bijective proof, where what if we want to show that there's n plus m choose m paths from the lower left corner to an upper right corner along the edges of an n by m grid using right and up steps. So first of all, if it's n by m, you'll see that there's a total of n plus m steps because you have to go m right steps and n up steps. And we can encode this kind of path from the lower left corner to the upper right corner with a sequence of directions. In this case, up, right, 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 up, right, right. And that tells our little robot to go up, right, 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 up, right. So certainly this is a bijection. The directions tell you uniquely what the path is, and the path has a unique set of directions. And so when we write it this way, then it's easy to see there's n plus m total u's and r's because there's n u's and m r's. And we just have to choose the position of where the u's are because any possible string of this many u's and r's is valid. So that's an example of bijective proof where we've taken our combinatorial object, used a bijection to write it in terms of something simpler, and then counted it over here. And then that means that this set has the same count. So now you try. Prove Gauss's lemma using a counting in two ways proof. As a hint, use the following diagram. This might help prove visually that 1 plus 2 plus 3 up to n is n times n plus 1 divided by 2. And that's all for today, and I'll see you next time.